So essentially what we're trying to do is we want to minimize polarization of the solution that we're trying to measure.
Wait, so starting from the top though, this is for your new EC circuit, your
Correct.
sample and hold thing?
Yes. This is the sample and hold schematic with all the standard schematic elements.
And so what happens when you are working with charged particles and stuff?
If you're working with charged particles and you have an anode and a cathode in solution, the opposite charged particles will be attracted to each electrode. And when that happens, you ultimately affect the solution that you're trying to measure, and this will then change your result.
Okay.
To avoid this from happening, you want to rapidly switch the poles, and this will tend to keep the solution more or less the same as it was before you came along and tried to measure it. So for our EC circuit here, we have a nominal voltage of 3.3 volts. So in this case, it makes the most sense to switch between 3.3 volts and negative 3.3 volts, as that's the supply voltage. We use this clock. This is our standard, I think it's the CD4030 from TI. It is a binary flip-flop counter. And what this does is you tie it to an RC circuit, and it will flip the lowest bit at a certain frequency, in this case 3,000 times a second, and then whenever that bit flips, goes from a 0 to a 1 and then back to a 0, the next significant bit will flip. And so this way you can count very large numbers, like let's say if you had a tipping bucket or something tied to it, you could use this to count. But in this application, we're using it to generate a square wave. Using this chip, having it be base 2 allows us to do a 3 kilohertz oscillation and a 1.5 kilohertz oscillation. We'll get back to that more in a little bit. Summing up the operating principle, we produce a square wave from 3.3 volts to negative 3.3 volts. That is symmetric about the voltage axis, about the time axis, at a frequency of roughly 3.0 kilohertz. This square wave passes through the solution that we're trying to measure, and whenever this voltage is applied to between two electrodes in solution, a current will flow between them. Let's pan over to this whiteboard. In total, we have 4 electrodes in solution. Electrodes A, M, N, and B. Our A electrode is where our voltage is injected. So we can say this is where our square wave goes into. This is going to naturally induce a current between our injection point and wherever our ground is. In this case, our B electrode serves as our ground. However, we also need to measure the amount of current that's flowing through our solution, and to do that, we add a shunt resistor of 10 kiloohms. This will naturally induce a current between A and B through our solution that we're trying to measure its conductivity. Because we know the resistance of our shunt resistor, we can measure the voltage right here at this node, and that will tell us the amount of current that is flowing through this circuit based on Ohm's law. So right now, up to this point, we've established that we have a square wave, 3.3 volts, negative 3.3 volts, oscillating, inducing current from A to B, and then of course when the polarity is reversed, from B to A. Ultimately, with this setup, we're trying to determine the resistivity of the solution. And of course, the inverse of resistivity is conductivity. And if you're familiar with Ohm's law, V equals IR. If we can know the current and we can know the voltage, we can calculate the resistance, the apparent resistance that these electrodes see in solution. Based off of how much current is flowing from A to B, we know the current part. But how do we get the voltage part, you might ask? You see, mechanically, each of these electrodes is a symmetric distance apart. That means we can also infer that between A and B, there's a constant voltage gradient. That when the A node is at 3.3 volts, the voltage will decrease linearly to our voltage across the shunt resistor at B. Of course, there's going to be a voltage drop across the shunt resistor due to the flow of current, but regardless, we should see a linear voltage gradient in this region. Because of this voltage gradient, if we take two arbitrary points in the middle, and we know their distances between A and B, we can measure the voltage drop, as node M is going to be at a higher voltage than node N when 3.3 volts is applied at A, as the voltage is the highest at node A and the lowest at node B, and the gradient will be followed as such. Our next step, after we've injected current at node A, let me erase these lines really fast. We can sample the current by measuring the voltage at node B, and we can measure our voltage gradient by comparing the voltages at node M and node N. Think about it as this. So at node A, we're going to have a square wave from negative 3.3 volts to 3.3 volts. As such. At node M, we're going to have a slightly smaller square wave. Say we put this in the same axis scaling. It's going to look something like this. It's a little bit smaller in magnitude than node A, but it's not quite ground. At node M, we're going to have an even smaller square wave. Something maybe like this. I did invert the phase in this drawing, but you get the idea.
You get the idea. Yeah.
If we were to subtract these two, we take this one, call it 1, and this wave, and call it 2, and we subtract them, we get a smaller square wave that represents the difference in magnitude between this wave and this wave. And this is going to represent our voltage drop. So once we know our voltage drop and we know our current, we can calculate our resistance based off of Ohm's law. Take the reciprocal, and that's our conductivity.
Write it out.
V equals I R.
So you're going to multiply.
Divide both sides by I,
Nice.
and we get V over I equals R.
Excellent.
Or I over V equals C.
Excellent.
They're equivalent expressions. That's the general operating principle.
All right. Fantastic. Thanks. All right. We're going to walk through the...
Yep. That's next.
Okay.
I'm pretty sure I'm going to need this space, so I'm just erasing it for